You're sitting on terabytes of valuable data, and every day you wait to analyze it, your competitors are making moves. Modern big data analytics can turn that raw data into actionable insights faster than you ever thought possible. Often at a cost so low, you'll wonder why you ever ran a traditional warehouse. In this video, we're breaking down the entire analytics pipeline, from real-time streaming to petabyte-scale analysis, using the best tools the cloud has to offer. And right now, you can sign up for a cloud provider's free tier and run your first analytics query on a public dataset without spending a dime. This week, not someday. That's how you beat the competition before lunch. Big data analytics isn't just about having a lot of data. It's about making sense of it fast enough to matter. The industry often defines it by the 5 V's: volume, the sheer scale of data in terabytes or more; velocity, the speed at which data arrives, often in real time; variety, encompassing structured tables, semi-structured logs, and unstructured video; veracity, the trustworthiness of that data; and finally, value, the whole point, turning all of the above into insights that drive decisions. That's where machine learning, statistical modeling, and distributed processing come in, transforming raw bits into strategy. Before we zoom in on any single technique, let's lay out the modern data architecture at a high level. First, data sources: web apps, IoT sensors, databases. That data flows into an ingestion layer, think messaging queues and real-time connectors, that collect and transport data reliably. Next, a processing layer, using stream or batch engines, cleans, transforms, and enriches the data. The processed data lands in a scalable data warehouse, or a lakehouse. A lakehouse combines the flexible storage of a data lake with the SQL query performance of a warehouse for storage and lightning-fast analysis. Finally, business users explore it through BI dashboards, and data scientists feed it into machine learning models. This is the pipeline we'll dissect piece by piece, using cloud-agnostic concepts that apply everywhere. Big data isn't just large spreadsheets. It's defined by the 5 V's volume. We're talking terabytes to petabytes. Velocity, data that arrives at high speed, like streaming sensor readings flowing in continuously. Variety, one pipeline might handle database tables, JSON logs, and video files. Veracity, with that much data, a lot of it is noisy or inaccurate. You have to clean it. And value, if you're not turning it into something that saves money or spots a new trend, you're just hoarding. Big data analytics is the process of extracting that value. Here's why the old way breaks down. Traditional on-prem data warehouses were built for structured, batch workloads. When you throw in terabytes of streaming data from IoT or social media, you end up with a rigid system that can't keep up without a massive hardware refresh. You're stuck managing servers, tuning indexes, and begging for budget. Cloud-native analytics flips the script. Compute scales independently of storage. You pay for the queries you actually run, and you can get insights from fresh data in seconds. That's the difference between drowning in maintenance and surfing on insights. Modern analytics engines separate storage and compute. Data sits in a durable, inexpensive object store that's optimized for columnar scans. The compute layer is a fully managed, serverless query engine that spins up thousands of parallel workers on demand. Between them sits a high-speed shuffle network. Shuffle is the process of redistributing data across those workers so that related records end up on the same worker for grouping and joining, avoiding a bottleneck. Because storage and compute are decoupled, They scale independently. You can run a 1,000-node query without touching the storage tier, and 10 analysts can fire off massive queries at the same time with no I/O contention. That's how you get petabyte-scale performance without petabyte-scale cost. Let's cement this concept. Time for a quick recall. What is the main advantage of decoupling storage and compute in a modern analytics engine? To speed up queries even more, modern warehouses use partitioning, dividing a table into date-based chunks. When your query filters on the last 30 days, the engine only scans the relevant partition, skipping older data entirely. Inside each partition, you can also use clustering to sort rows by columns like user ID. Then a query that filters on both date and user ID can further skip entire blocks within the partition. Think of it like organizing books by genre, partitioning, then alphabetizing by author within each shelf, clustering. You find what you need without scanning the whole library. If you've ever tried running a complex analytics query on a production MySQL or PostgreSQL database, you know the pain. Minutes of waiting, heavy CPU load, and your users notice. That's because OLTP databases are built for short, fast transactions, not scanning billions of rows. Analytical workloads need an OLAP engine, designed from scratch for massive reads. It uses columnar storage, runs queries in parallel on thousands of cores, doesn't rely on indexes, and separates storage from compute, so you never have to upgrade a box. That's why the analytics workhorse stays separate, and your transaction database keeps doing what it does best. Big data analytics commonly relies on several core methods. Descriptive analytics answers what happened by summarizing data. Diagnostic asks why it happened by drilling into causes. Predictive uses machine learning to forecast what will happen. Some frameworks add a prescriptive layer that recommends actions, but the foundational three are these. Together, they transform raw data into strategic insight. Understanding the four methods isn't just academic. It's what moves you from a reporting dashboard to a decision engine. Descriptive tells you sales dropped 15%. Diagnostic reveals it was a failed marketing campaign. Predictive estimates the revenue hit next quarter. Prescriptive recommends the coupon strategy most likely to recover. That's the progression that turns a data analyst into a business partner. Time for a quick checkpoint. The 5 V's of big data are volume, velocity, variety, veracity, and the most important, value. If data doesn't generate value, all the volume in the world is just noise. The volume and velocity of data today is staggering. As data streams grow, the ability to process real-time information becomes essential. That's the real-time imperative that drives modern architecture. Tools like GCP's PubSub can ingest millions of events per second, making real-time processing not just feasible but standard. Quick check. Why is real-time processing critical for a large fraction of today's data? Because data from streams like IoT and financial transactions loses its value quickly. You need immediate analysis to drive decisions, detect fraud, or personalize experiences. Here's the distinction in practice. Descriptive analytics gives you the dashboard. Sales by region, revenue by product. Diagnostic analytics goes further. It tells you that sales in the West are down because your top competitor ran a price promotion. That's the leap from monitoring your business to actually understanding it. Big data isn't just a lot of data. It's defined by 5 key dimensions: volume, velocity, variety, veracity, and value. turning all of it into actionable insights that move the business forward. Now we shift to the nervous system of a big data pipeline. Real-time ingestion. Data streams in continuously from sensors, click streams, and log files. To handle this velocity, a message broker decouples producers from consumers. Producers send messages to a topic, and multiple consumers can receive copies independently. This decoupling lets you add, remove, or scale consumers without touching upstream code. It also buffers data when downstream systems fall behind. An essential pattern for resilient, event-driven architectures. Message brokers bring 3 key benefits to big data pipelines. Fan-out lets a single incoming message reach multiple listeners without extra publisher logic. Buffering smooths out traffic spikes and keeps messages safe when consumers are temporarily down. Retention policies let you tune how long they're kept. And brokers are built to scale. They can absorb high-velocity streams, making them the backbone of real-time analytics without you ever having to provision capacity. Here's where many architects hit a wall. Thinking real-time and batch data need completely separate systems. In reality, you can unify them with the right ingestion pattern. Streaming ingestion pushes each event immediately, ideal for live dashboards and instant alerts, while batch ingestion collects events over a window and processes them together, giving you higher throughput and cost efficiency. Both approaches power modern cloud analytics stacks, and knowing when to use each is the difference between a fast pipeline and a double-budget hit. Stick around. Next, I'll unpack the message structure that makes this possible, and the one design rule that prevents duplicate data nightmares. Let's break down a typical cloud messaging message. Every message carries a data payload, the event bytes, and optional key value attributes that add metadata without touching the payload. Because distributed systems can deliver a message more than once, your subscriber must be idempotent. Processing the same message twice shouldn't change the outcome. Typically, once all intended consumers have successfully processed the event, the message is considered delivered and can be removed. That's the pattern that keeps pipelines clean. Let's test your knowledge. Before we move on, let's lock in the message queue concepts. Checkpoint. Let's test your understanding of the fan-out pattern. When moving batch and streaming workloads to the cloud, the choice of engine matters. Apache Spark is an open-source distributed processing framework built for high-speed analytics on huge datasets, capable of both batch and streaming. If you already have Spark code from on-premises, a managed Spark service like Dataproc can run it with minimal changes, on-demand clusters, paying only for what you use. For brand new pipelines that demand low latency, event-by-event processing with exactly once guarantees, a serverless stream processor like Dataflow is the right call. It unifies batch and streaming without any cluster management. The rule: reuse your existing Spark investment, but start fresh with stream processing for real-time needs. A typical analytics pipeline breaks down into 4 stages, regardless of which cloud you use. First, ingestion. Streaming and batch data from apps, IoT sensors, or databases pour in. Second, processing. Engines like Apache Spark or Apache Beam, an open-source programming model that unifies batch and streaming pipelines, filter, aggregate, and enrich the raw data. Third, the cleaned data lands in a scalable warehouse or lakehouse, ready for SQL analysis. Finally, BI tools connect to that warehouse to deliver real-time dashboards and reports. So you'll see the flow as ingestion, processing, storage, and visualization. That's the backbone of many modern analytic stacks. Time for a retention drill. What are the main stages in a typical analytics pipeline? Pause and recall. They often include ingestion, processing, storage, and then analysis and reporting. Raw data flows from sources through processing engines to a data warehouse or lake, then to BI dashboards. Remember, this pattern is a foundation, not a strict rule. Real architectures can add more layers. Streaming inserts aren't a feature every cloud data warehouse offers, but platforms like Google BigQuery do. With the Storage Write API, your app can push rows directly into tables and query them within seconds. This turns a warehouse from batch-only into a near real-time analytics engine, giving you live dashboards, instant anomaly detection, and real-time personalization when paired with a message queue like PubSub. The classic beginner mistake, assuming your warehouse can only load data in batches. Check your provider's streaming ingestion API. If it's there, you can act on events almost instantly. You'll pay for storage like any other data, but the real advantage is combining fresh and historical data in one place without extra infrastructure. Let's zoom out and recap the entire cloud analytics stack. A message queue service ingests and buffers streaming data. Your entry point for event-driven architectures. A stream processing engine or a managed Spark service for existing Hadoop jobs processes that data in real-time or batch. Quick refresher. Apache Spark is an open-source distributed processing engine, and Hadoop is an ecosystem for distributed storage and processing. A cloud data warehouse then stores and analyzes it at massive scale with standard SQL. And a BI tool tops it off by letting business users explore visualizations without code. Together, these services form an end-to-end, serverless, and infinitely scalable analytics pipeline. One that grows from gigabytes to petabytes without you ever managing a server.